real-time transport protocol. It is mostly used for entertainment because it takes a bunch of different data streams and shoves them together in the network and then pushes them through, and then they get they unfold. Error treat specially. Let's see here. It's used a lot for like media center stuff. So if you're doing a video and you have surround sound, each of those speakers has a separate channel that takes separate input, and that's denoted by the source identifier and also the contributing source identifier. Each of those can separate it out, so you can have a bunch of audio being pushed through the network, and then it's all split up into each different one. And this is just a diagram of how the header or the packet is put together. So it comes from the multimedia application, calls the RTP protocol, puts in the payload, does all of that, then it goes down to the UDP, then to the IP, and then to the Ethernet. It's pretty specialized and only really used in media center applications. And with that, off.
Okay, so real-time transfer control protocol works hand in hand with RTP. What that's concerned with is, say your bandwidth is changing over the course of the time you're streaming your media, which happens fairly often. What do? What RTCP does is it lets you provide continuous feedback. So you can say over the course of the streaming period, do I need to, well, I'll use YouTube as an example. If, say, your bandwidth gets lowered, what happens on YouTube? The encoding, it goes from, like, say, 480p to 360p. And so you're sending less data. So what happens is this happens over a period of time. You don't send an RTCP header every single time you send the packet or a segment, because you're doing this for a bunch of users at one time. You don't need to update every single time a segment is sent. You just need it once every certain length of time. RTCP is also used for synchronizing time, so the clocks on different systems aren't necessarily the same time, and RTCP can help synchronize that sort of thing. Next is jitter control. So there's always a delay a delay in the data sent when it goes from host to client. But even if they're sent by the host at the same time, the delay won't necessarily be the same. So how do we know when to start playing this media if the delay is varying and you aren't guaranteed a certain amount of delay? Because if the delay increases, the variance is going to increase, and that just leads to a whole bunch of problems. The way we can do that is with jitter control. There are two solutions to this problem. One of them is buffering, and then one of them is just skipping over the packet. And in this diagram, I don't know if you guys can see it, but I guess, in this one, the first 7 packets are received by the time they need to be played, but this 8th one isn't received at a certain time. They have two choices here. You can either buffer again, or you can just skip over it. Now, if you're streaming like a Skype message or something, you probably want to skip over because, like we talked about earlier, you don't want to necessarily play it back after it's useful. But if you're watching a YouTube video, you're listening to music, you're more concerned about the quality of that, and you'd rather wait for this to come than just skipping over it. Now, it is UDP, so after a certain point, you might just have to skip over it because you're not necessarily guaranteed to get that back. It could be lost. But that's jitter control. And we did implement the buffering part of jitter control, and that's